What is going on, guys? Welcome back. In this video today we're going to learn about construction heuristics and we're going to solve the traveling salesman problem. We're going to also visualize the solution using such a construction heuristic. So let us get right into it. Alright, so before we get right into the code, I would like to cover the theoretical aspects of this video a little bit so that we understand what we're actually doing. And I'm going to start by explaining the TSP. So the TSP is the traveling salesman problem. It's easy to understand, but not so easy to solve. So the idea is you have certain positions, for example, different cities in Europe, different cities in the United States, or just positions that you want to travel to. And you want to travel to all of these positions and end up where you started in the most optimal way. So for example, we might have a city here, we might have a city here, here, whatever. Just imagine this to be a map. And the goal is now to get from maybe here back to here and travel through all these different positions. And, you could start to just go in an inefficient way and end up here, and this would probably not be the best solution. And then you could try to also find the optimal way. So considering this to be an actual geometric problem, so those are the actual distances, you would just try to find the way that is the shortest way. Now, if we want to express this as a graph theory problem, we could have different nodes. Let's say we have 4 nodes, 4 positions, 4 cities, whatever, and we could consider this to be a complete graph. So every node is connected to every other node, and I can travel from each node to every other node. Now, these connections have certain weights, let's say, so certain cost to them. So traveling from here to here has a cost of 5, for example. Traveling from here to here has a cost of 1, for example. Traveling from here to here has a cost of 3, for example, and so on and so forth. So we have a certain cost associated with these particular edges. And the goal is now to get from, let's call this A, from A through all these other nodes back to A, and to find the optimal path. So that is the basic TSP problem. Now, to solve this TSP problem, this problem is a problem which is called NP-hard. I'm not going to explain what this basically, what this means exactly, but this essentially means that it's a very hard problem to solve. Every algorithm that finds the optimal solution will probably have exponential runtime. At least this is what we assume at the moment. This goes back to the idea of P being equal to NP question mark. We don't know yet. Goes too much into the details of algorithmic complexity here. But the TSP is the problem that we're going to solve in this video today. Now, you have basically 3 ways. We could say we have 3 major ways to solve that. We can find the optimal problem using a very inefficient algorithm, at least at this point in time. And we can have an approximation. An approximation basically means we have a quality guarantee, so we know that there will be a certain level of quality, but we might not get to the optimal solution. We will probably not get to the optimal solution, but we will have a quality guarantee. And then there's also the way of the heuristic. And a heuristic is basically the idea that I don't have a quality guarantee. It's very similar to approximation, but I don't have a quality guarantee. But usually I get to a good solution, to a reasonably good solution in a reasonable amount of time. And this is what we're going to focus on in this video today. We're going to use a heuristic. We're going to we're going to use a so-called construction heuristic. And this construction heuristic basically means we're going to construct the solution. So we start at node A, we have node B, C, D, and so on. And we know the weights of these connections. And what I'm going to do, I'm going to start at A and I'm going to pick. So let's draw this briefly here again. If I have, for example, here the cost of 2, 3, 1, I'm always going to go the greedy way of taking the nearest neighbor. So that would be a nearest neighbor construction heuristic. Then maybe from here I have a connection 2, 4. I would go to the greedy one again. So I would go to B. And then maybe here I have 5 or something. So from B, I cannot go to A, or it doesn't make sense to go back to A. So I would go to the other possibility that I have, which is this one here. And then you would basically try to find the best way to end up at A again. So this is just an example. Now we're going to use more complicated graphs. So that is the theory on paper or in my paint here. Now we're going to put all of this into code, and we're going to animate the process so that you can see what is happening. And for this, we're going to write Python code. So let me just put my tablet aside. And we're going to have to install a couple of packages, or actually just 2 packages. So we're going to open up a command line, pip reinstall. We're going to install matplotlib for the visualization, and we're going to install the package called networkx, which is a package that makes it very easy to work with graphs, to add edges, to add nodes, to calculate certain things, to get a complete graph and something like that. So what we're going to do now first is we're going to import networkx as nx, which is the usual alias. We're going to import matplotlib.pyplot as plt. We're going to also import the core Python package random, and then later on we're going to import something else, but for now this is going to be it. And we're going to start by defining a function that creates a random complete graph, just so we have the problem to solve. And we don't want to solve always the same problem, so we're going to generate a complete graph which is random. Complete meaning every node is connected to every other node. So we're going to call this generate complete graph. And what we're going to pass here is the number of nodes and the weight range, which by default we're just going to set to 1 and 100. Meaning that the weights, the randomized weights, can be between 1 and 100 for the connections, so the cost of the connections. The graph itself will be just nx.completeGraph. This is a function provided by networkx, which generates a complete graph with a certain number of nodes, which is our parameter. And then we're going to say for every connection, for every edge in graph.edges, what we're going to do is we're going to assign a weight to this particular edge. So we're going to say g edges uv. The weight of that connection will be a random number, so random rand int, and the range is going to be the weight range. We're just going to unzip it here. This is the fancy way of doing it. You could also just say weight range 0, weight range 1, but we're now unzipping this, basically having the same effect here. And what we want to return is the graph. So that is already the graph. Now I can actually run this, generate complete graph with 5 nodes, and the weight range is just going to be default. And I can print the result. I'm not sure what happens when I print a graph. Okay, it just tells me what the graph looks like, but maybe I can go to edges and see what the edges are. Yeah, this is the graph defined as an edge list here. So this is what we're going to use to solve the problem. We have certain weights, and we are going to find the optimal way from the starting point to the end point. Now, before we get into the solution, into the heuristic, we're going to define a method to plot the individual steps. So we're going to call this plot graph step to plot the next step that we take so that we can visualize the process. And this is going to take a graph as a parameter. It's going to take a tour as a parameter, meaning what has happened up until this point, what's the current tour that I have, then also the current node that I'm at, and the position argument, which is important just so we have the same plot of the graph. So the position argument is not really something you have to care about. It's basically just when you plot a graph, the nodes can be spread out in different ways, and by keeping the same position, we get the same graph structure visually. Doesn't change anything about the graph itself. So first of all, we're going to clear the current plot if there is something. So we're going to clear the figure. Then we're going to say nx draw. So we're going to visualize the graph itself, given the position, which is what I just explained, with labels being true, meaning we also plot the node labels so that we know which one is which one. We're going to say that the node color is going to be a light blue. You can also, of course, change that. And we're going to say that the node size, again, just a visual thing, is going to be 500. So let me just zoom out a little bit. And then we're going to say path edges is going to be equal to list zip. And then we're going to basically take the tour, the full tour, and tour 1 until the end. Now, what's the effect of that? I'm going to show you a brief example of this. The basic idea is if I have a list that describes my path, so let's say I have tour, and in this tour I went from 1 to 3 to, from 1 to 2 to 3 to 4 to 5, that is my tour. If I say list zip tour and tour 1 until the end, what I basically get is the path. So 1 to 2, 2 to 3, 3 to 4, 4 to 5. So basically a graph that is a path. That's the reason why we do this here, so that we can visualize the path that we took. Then nx.draw network edges. We're going to draw this path that I just explained how we create. So g position edge list is going to be equal to path edges, which we just computed. And we want to show this as a red color. So the path is going to be a red path. And we're going to say the width of this path is 2. Now let me just add some space down here so that I can code up here. And then we're going to also say the current node needs to be highlighted so that we know where we're currently at. And we're going to say g position again, and node list is going to be just the current node. And we're going to say node color of this current node is going to be equal to green. And of course, we don't want to draw the edges. Draw network nodes is the function. And the node size is just going to be 500 again. So that's that. Then we also need to add the edge labels. So we're going to say edge labels is going to be equal to nx get edge attributes. And from the graph, we want to get the weights, just so we have everything in our visualization so that we can see what's actually happening. And then we're going to just say nx.draw network edge labels. And here we're going to just say g position edge labels is equal to edge labels. So we're just showing the weights. And we want to say PLT pause because that is going to be an animation. So we're going to see the actual process of the construction. And for this, we have a delay so that we can follow the steps. Otherwise, it's just going to happen instantaneously. All right, so that is our plot graph step function. Now, one more thing before we get into the actual construction heuristic is we're going to define a cost function just so we can keep track of the quality of the solution. So calculate tour cost. And we're going to pass g and a tour. And we're going to just say return the sum of g tour I. So this is going to be now a list comprehension. So tour I. And then tour I plus 1. And from that, we want to get the weight. So this connection, we want to get the weight of this connection. So basically, we have in the tour that I showed you, we have these edges representing the path that we took. And now we want to get the weight of each of those edges that we chose, sum them up, and that is going to be our cost, obviously. For I in range length tour minus 1. So we just iterate over the edges and we calculate the cost, which we get from the graph itself. All right, so that is the setup. Now we're going to implement the actual construction heuristic. We're going to call this now nearest neighbor TSP. You can also call this nearest neighbor construction heuristic or whatever you want to call it. We're going to pass the graph and a start node, which by default will be none, so that we have also the possibility of a random start node if we don't specify one, which is the first thing we're going to define. If start node is none, just choose a random start node by saying start node is random choice list g nodes. All right, so we start at some point, either we pass it or we just get it randomly. And then we're going to, first of all, design or define the position of the graph. This is, again, just for the visualization. This is not relevant for our actual construction heuristic. So we're just going to say position is nx spring layout. This is just so that the graph is displayed a certain way. Then we're going to say PLT I on, interactive mode is going to be on, PLT show. And then we're going to actually start heuristic. And in between, we're going to plot the individual steps. So what we're going to do first is we're going to define unvisited nodes are going to be the set of nodes that we have. So all nodes in the beginning are unvisited nodes, except, of course, for the start node. So we're going to say right away unvisited remove start node. So all the nodes except for the starting node are unvisited. So we need to go to them. And then we're going to say that the tour is an empty list in the beginning, but not exactly because we start at the start node. So the tour is the start node at this point. And then we're going to say the current node that we are at is, of course, at this point in time. So when we start is the start node. So the current node is going to be equal to the start node, and this is going to change, of course. So in the beginning, we have just a start node, and we want to visualize that. So what we're going to do is we're going to say plot graph step. So plot graph step. And in the beginning, we have just the basic graph, the full graph that we want to plot. The tour is just going to be our starting node. The current node is our starting node, so it's going to be highlighted in green. And that is it. So we plot this step. Now, while we have unvisited nodes, so nodes that we still have to visit in our tour, in our TSP tour, while this is the case, we're going to say that the next node that we want to visit is going to be the greedy nearest neighbor, meaning the closest node to the node I'm currently at. How do I do this? I just use the the min function on the unvisited set, and the key to determine what is minimum, because that is just a set of nodes, is going to be a lambda expression, so a function where I get the node and I just get the weight of the connection from the current node to the node from the graph. So it's going to be basically current node to node, and from this I want to get the weight. So just to explain this again, what we're doing is we have the list of nodes that we can visit, or the set of nodes that we can visit, and we apply this function as a criterion. We want to minimize that function, so the function is the weight between the node we're currently at and the node we want to go to, and we pick the one that has the minimum weight in the graph. So that is our next node. We remove this node from the unvisited set, and then we say tour append this node. And then we set the current node to this next node. So it's no longer the starting node, it's now this next node. And then, of course, we plot this step. So G tour current node position. All right, and in the end, when we're done, we're going to again append the start node, because of course you're gonna go full circle. You wanna come back where you started. That's the idea of the TSP. And then of course we wanna plot this again. So current node position. What I also wanna do is I wanna print the actual tour as text so that I can see it. And I wanna also calculate the cost. So the tour cost is going to be calculate to tour cost, and I want to pass the graph into tour, and then I want to print the result. So heuristic, or maybe construction heuristic, tour cost, and this is going to have the tour cost of tour cost. Then I want to turn off the interactive mode, and I want to show the graph finally, and then I'm going to also return, or actually I don't need to return the tour. I can just do everything in here. All right, so that is the heuristic, and what we can do now is we can say if __ name equals __ main __, and then I can just say number of nodes is going to, or actually I can pass this right away. I can say G equals create complete graph, or what did I call it? Generate complete graph with 5 nodes, for example. And then I can just run the heuristic. So I can just say nearest neighbor TSP on the graph, and the start node is going to be just 0 in my case. So I'm not going to leave it to chance. I'm going to pick 0 as the start node, and then you can see what happens here. So now, basically my tour was going from, and actually my weights are not displayed. Why is that? Let me just check why this is the case. Oh, I can see the actual problem. The problem is I'm using weights here as a keyword, even though I should be using weight. That should be the problem. And now you can see it works. So I have this complete graph, and the path in this case was now from 0 to 3, because of course that is the cheapest connection from 0 to 3. Then from 3 I go to 2, because 71 is less than 94. From 2 I go to 1, and from 1 I go to 4, and from 4 I go to 0. So that would be one TSP solution. The cost of that would be 174, just adding up all the weights here, or all the cost here. And of course, if you have a different concept, you can also say, I don't want to minimize the cost, I want to maximize the reward. And you can say that the weight that I have here for the individual edges is the reward, so I want to maximize this. And the only thing that you would have to change here is actually you have to change this min to max. and then you would get always the maximum path. So here I can go, I will always maximize, in this case, not the cost, but the reward. But let's keep it at minimum. And what we can do now, finally, is we can also add a comparison. So we can also use something from network X directly, which is from network x.algorithms.approximation. We can import the traveling salesman problem, and this is going to use an approximation algorithm. So I think it has a quality guarantee, if I got this correctly. We can use that to compare it to our solution. So what we can do is we can say approximation tour is going to be equal to traveling salesman problem on the graph, cycle being equal to true, meaning we're coming back to where we started, and then approximate tour cost is going to be equal to calculate tour cost, approximate tour, and then we can just print the tour and the cost, which of course happens for our solution in the function. So what we get here is, this is the tour that the approximation algorithm ends up with, and this is the cost, and this is our tour and our cost. In this case, we perform worse than the approximation, which is not surprising because this greedy construction heuristic is not a very reasonable way to do it. There are better construction heuristics as well. Now we have the exact same cost, even though we have a different tour. We can run this a couple of times. At some point, we might outperform it, actually. Right now, it's not the case, but I had the situation where I outperformed it. So it can happen that the heuristic that we have here is actually better than the approximation. Now it was 2 times, it was exactly the same. I can keep trying a little bit. And of course, we can also increase the nodes. So the number of nodes that we have here to make it more complex. So again, we get the same here. Let's go with 10. I'm not sure if this is going to lead to better results for us or to worse results. I suspect the latter, but let's see. Yeah, I mean, most of the time we don't outperform the traveling salesman problem approximation algorithm. But again, as I said, this is a greedy construction heuristic, so it's not necessarily the best way to approach the problem. There are many other heuristics and local search methods and stuff like that that can make your solution much better and probably outperform this function here. We can try with a smaller graph. Maybe we can make this happen at least once. But it doesn't seem like that. I can just tell you that I had this situation once. So let me try 2 more times and then we're going to stop. This was way worse now. Okay, no, we end up with the same result sometimes. Okay, so that is how you implement a construction heuristic to solve the traveling salesman problem in Python. Again, why do we even do that? Because the optimal solution is hard to find. Now, for a small graph like the one we used, probably not. But if we have 1,000 nodes, or if we have just 100 nodes, you can see what this looks like. Probably you won't see it because my recording will crash. So let me just decrease this to 50. Still very, yeah, you can see what happens here. So it's not really, if you go to the thousands and 10,000s of nodes, it's becoming quite complicated. So heuristics and approximation algorithms are the way to go here. And this was a very simple way of constructing or of using such a construction heuristic. So that's it for today's video. I hope you enjoyed it and hope you learned something. If so, let me know by hitting the like button and leaving a comment in the comment section down below. And of course, don't forget to subscribe to this channel and hit the notification bell to not miss a single future video for free. Other than that, thank you much for watching. See you in the next video and bye.